We are diving into the technical report for MiMo-Embodied, X-Embodied foundation model from the Xiaomi Embodied Intelligence team. And this paper, it feels like a genuinely monumental step in generalist AI.
It really is. MiMo-Embodied is a real breakthrough because it's the first open-source, cross-embodied foundation model that successfully merges two domains we normally keep very separate: autonomous driving, or AD, and general embodied AI, EAI.
And the technical achievement here is just, well, it's undeniable. We're talking about a single unified model that's achieved state-of-the-art SOTA performance across 29 different benchmarks.
29. And that's 17 for EAI, so things like spatial reasoning and manipulation, and then another 12 for these incredibly complex AD scenarios.
Wow.
And here's the core takeaway for any researchers watching. The paper gives us actual quantitative proof of a strong positive transfer. I mean, the skills learned in one domain actively reinforce the skills needed in the other.
And that synergy wasn't an accident.
Not at all. It was engineered. They used a really sophisticated multi-stage learning strategy that brought in chain-of-thought reasoning and even reinforcement learning fine-tuning.
That idea of mutual reinforcement is so key because traditionally we've just seen this massive fragmentation in embodied VLMs, right? You have your indoor specialist models like RoboBrain or VBrain, which are hyper-focused on tasks inside a house or a lab.
And on the other side, you have the outdoor specialists, your Robotron drives or Drivel LMM1s, which are all about high-speed, multi-agent driving on highways.
The problem has always been that fundamental domain gap. An indoor model is all about fine motor skills in cluttered scenes, while an outdoor model needs, this rapid, broad perception.
Exactly. So the community has been struggling to find a unified approach that can generalize things like spatial understanding across these wildly different physical environments. It's like trying to train someone to be a world-class surgeon and a fighter pilot at the same time.
A great analogy.
And MiMo-Embodied was designed to be that bridge. They identified 6 key capabilities, 3 for each domain, that had the potential to overlap and really benefit each other.
Okay, so let's break that down. Looking at the EAI side, the indoor robotics, what skills were they targeting?
The focus was all on precise physical interaction. So first you have Affordance Prediction. That's the model figuring out actionable possibilities, like where exactly to grasp a tool.
Not just what to grab, but how.
Precisely. Then second, task planning, so turning an abstract command like clean the table into a concrete sequence of actions. And third, spatial understanding, comprehending 3D relationships, direction, distance, all that.
And then for the autonomous driving side, the capabilities had to mirror that, but I guess at a different scale and speed?
They're very much aligned. You've got environmental perception, so scene comprehension and hazard ID. Then status prediction, which is forecasting what other cars or pedestrians are about to do. And finally, driving planning, which is generating safe maneuvers with justifications.
That makes sense on paper, but I'm still trying to wrap my head around it. I mean, how did they stop the AD tasks, which need these fast, broad strokes, from just completely cannibalizing the precision needed for the indoor EAI tasks?
That is the central challenge, and it's why their training strategy is so critical. But before we get to that, the architecture itself is built on their existing MIMO-VL framework. It's got 3 core components.
The foundation.
The foundation, exactly. First, a vision transformer, the VIT, which is the visual backbone. It handles images, videos, multi-view feeds, and so on.
Then you need to connect that vision to the language part.
Right, so that's the projector. It's an MLP that maps all those visual tokens into a latent space the language model can actually work with.
And the third piece is the brain of the operation, the large language model, which also came from MIMO-VL.
Yep, that's what handles the text understanding and the complex multimodal reasoning that bridges everything together. So they started with a really strong VLM base, but the real magic came in how they taught it, the specialized physics of these two worlds.
Okay, so let's talk about that training. This is where the complexity really is. To get this cross-domain skill, they needed this huge, very structured data set broken into 3 big categories.
Right. First, you have the baseline general data set. That's from MIMO-VL. And it just establishes foundational skills, visual grounding, video comprehension, stuff like that.
And then came the specialized pillars. They started with the Embodied AI data set, which was built specifically for those affordance planning and spatial tasks.
And they had to be so specific here. For affordance, they used data from Pixmo points for fine-grained localization like Teeking It, where on an object to touch and robo-afford for understanding the larger scene context. And critically, they used things like Robo Fit to handle ambiguity.
So it can distinguish the blue cup from the red cup on a messy desk.
Exactly. And for planning, they use Cosmos Reason 1 for intuitive physics, Ego Plan IT for first-person action prediction. And for spatial tasks, which are just non-negotiable, they curated a bunch of 3D datasets like Scooty 3D to really nail down monocular 3D understanding and navigation.
So a super deep dive into the messy indoor world. And then they had to teach it the dynamic, multi-agent chaos of the outdoor world with the autonomous driving dataset.
Yes, mirroring the same structure. For perception, they pulled from datasets like CodeLM and DravLM.
Yeah.
But the key wasn't just general scene understanding. They really targeted fine-grained localization in critical situations like the rare, high-risk corner cases you find in the drama dataset.
What about the decision-making data?
That was split into prediction and planning. So prediction data was all about anticipating others' movements. Will that car change lanes? And planning data was about generating the action and justifying it. They used data sets like NewInstruct that require the model to give an explicit, interpretable reason for its maneuver.
Okay, so now we get to what you call the secret sauce, the 4-stage progressive training strategy that actually made this all work.
This is it. This is the curriculum learning that makes it all possible. Stage 1 was EAI supervised fine-tuning. They started here. They grounded the model in physics and manipulation using the general data, plus all that specialized EAI data.
So it learns to walk before it learns to drive.
A perfect way to put it. Once that indoor foundation was solid, they moved to stage 2, AD-SFT. This is where they specialized the model for driving, focusing on multi-view spatial reasoning processing, 4 camera views at once, and maintaining temporal consistency across fast-moving video. It's a whole different ballgame from indoor reasoning.
And stage 3 was about making the whole process transparent, right?
That's chain of thought reasoning, SFT. This stage is purely about enhancing logical coherence. They trained the model to generate explicit reasoning chains. For AD, that might be breaking down a merge into risk assessment, speed check, lane confirmation.
And for EAI, it would be like breaking down make coffee into finding the mug, then the machine, then the water.
Exactly. And then finally, stage 4, where they brought in the heavy hitters. Reinforcement learning.
Stage 4, RL fine-tuning.
They used an algorithm called Group Relative Policy Optimization, or GRPO. This is the final polish. It's all about optimizing for precision and reliability, especially on safety-critical tasks. And they used rule-driven rewards. You get rewarded for an exact match on a question, or for a really high intersection over union IOU score on a spatial grounding task. It forces the model to be razor-sharp where it absolutely has to be.
And the result of this whole 4-stage curriculum is, frankly, pretty staggering. Let's look at the numbers, starting with the embodied AI performance. How did it do in the indoor world?
It was just dominant. In Affordance Prediction, SOTA on all 5 benchmarks they tested. But what's really telling is the margin. It was significantly better than other big models like RoboBrain 2.0 on metrics that mirror fine-grained interaction. So MiMo-Embodied doesn't just know what to grab, it knows the optimal point to grab it.
What about its ability to reason over longer tasks?
For task planning, strongest performance on RoboVQA, which needs complex causal inference. And for spatial understanding, it hit SOTA on comprehensive benchmarks like CV-Bench. This proves that the unified approach actually enhanced its ability to handle complex 3D indoor scenes.
Okay, so now let's flip the switch. Autonomous driving. How did this generalist model hold up against the AD specialists?
It held its own, and in many cases actually surpassed them. For perception, it did great across the board, but it really excelled in safety-critical local perception, so localizing objects in really complex scenes from drama, or identifying high-risk corner cases from CodeLM.
Which suggests those precision skills from the EAI training are directly transferring over, and for the critical task of actually making a decision.
It showed consistent superiority on crucial planning benchmarks, DriveLM, BDDX, NewInstruct. And this isn't just about predicting a smooth path. It underscores the model's ability to make decisions that are context-appropriate, safe, and importantly come with that interpretable reasoning that aligns with traffic laws.
Which brings us to the qualitative results. Let's move away from the numbers and see this intelligence in action, starting with embodied navigation.
Right, so the tests here required actual inference. For example, the command, I want to sleep. The model has to do 2 things. First, infer the target region, which is the bedroom, and then precisely localize the target object, the bed, from the robot's point of view.
And the visual comparisons they show against models like GPT-4o and RoboBrain 2.0 are really telling.
They really are. In these localization tasks, competitors often gave back these scattered points all around the object. But MiMo-Embodied, because of that tough RL fine-tuning with the IOU rewards, it consistently nailed the precise center point.
And why is that center point so crucial for a real robot?
Well, because if your navigation goal is off by even a few centimeters, your grasp will fail. It's the difference between grabbing the handle of a screwdriver versus grabbing the blade. Precision is everything.
They also pointed out its advantage with implicit language. You ask it to water the plants, plural, and it successfully identifies and localizes both plant pots in the room.
Yeah, whereas other models might just find one. That superior reasoning was also clear in the affordance prediction for manipulation. It consistently identified the correct functional interaction points on tools, or even found appropriate intermediate places to set an object down. It understands the physics of the action, not just the pixels.
Now let's move to the real-world driving validation. They used the public Navisim benchmark, which is about predicting a 4-second future trajectory from a single image.
And in that evaluation, the model just significantly outperformed comparable RL-based planners like Wreck-It Drive. It was way better on key safety metrics like the no-at-fault collision rate and drivable area compliance. It's direct proof that the COTI and RL stages translate into safer decisions.
And looking at the actual scenarios they show, we're talking complex stuff. Executing a U-turn on a curved road, a tricky lane change to overtake someone.
And what sets the MiMo-Embodied output apart is that it gives you the reasoning along with the trajectory. It doesn't just turn. It says, goal is left turn, traffic clear on left, initiating lane change to prepare.
Yeah.
That's huge for trust and for debugging these systems.
They also tested this on their own proprietary data, right? To validate it wasn't just good at the public benchmarks.
Yes, and on their most complex safety-critical scenarios like detouring around vulnerable road users or making tight lane changes, it showed a mean relative performance jump of 7.7% over their baseline. The biggest gains were always in those messy interactive maneuvers where the stakes are highest.
And all of this success really does hinge on that progressive training structure. The Ablation study, which is kind of buried near the end of the paper, is the quantitative proof.
It's the most critical piece of evidence in the whole report, I think. They found that if you just combine the training, throw all the EAI and AD data in a blender, you get clear task interference. The complexity of the driving tasks actually made the model worse at AD perception and planning.
So the domains were fighting each other.
They were competing for capacity. But the progressive multi-stage strategy didn't just prevent that interference, it created synergy.
And the numbers back that up.
Absolutely. The final MiMo-Embodied model saw a 4% average gain in EAI performance and an 8.1% average gain in AD performance, all compared to that naive, failed combined approach. It's the ultimate validation of their whole method. The order you teach things in really matters.
So they've proven this concept of unified embodiment works and is beneficial. What's next for the Xiaomi team?
Their plan is all about closing the loop to action, so developing vision language action, or VLA, models for both domains to enable more direct task execution. And they also plan to integrate 3D point cloud data to improve long-term planning, which is really the logical next step for true robustness in the physical world.
So MiMo-Embodied has done more than just sweep 29 SOTA benchmarks. It proves that combining the learning of indoor robotics and outdoor driving isn't just an interesting idea, it's a mutually beneficial engineering strategy. It sets a new, very high bar.
It really does. It proves that this kind of shared cross-domain intelligence is achievable, but only through very thoughtful data curation and, crucially, that structured multi-stage fine-tuning. The complex reasoning learned in a precise indoor context directly reinforces the safety skills needed in a dynamic outdoor one.
So here's a final thought to leave you with. Considering the incredible success Xiaomi found by unifying indoor robots and outdoor vehicles, what unseen safety or efficiency benefits might be unlocked if we started treating all our generalist AI systems, from desktop assistants to factory robots, as sharing a single, unified, embodied foundation? That's the question this report really leaves us to think about.